Assalamu alaikum. Bismillahir-Rahmanir-Rahim. I welcome you to the 36th lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, I will give you an example of invalidation scheme which we introduced last time, and then we will be talking about the coherence in distributed memory architecture. At the end, we may be talking about the performance of cache coherence schemes. Last time, we discussed the sharing of cache for multiprocessing in the symmetric shared memory architecture. Here we discussed that the private and shared data have their role in the cache coherence determination. The data value which is being used by a single processor is referred to as the private data, whereas the data which is replicated in the caches of the multiprocessors for their simultaneous use is referred to as the shared data. Last time we discussed the cache coherence problem in the symmetric shared memory architecture, which results due to the inconsistency or say the conflict in caching or shared data being read by multiple processors simultaneously. Here we studied the cache coherence problem with the help of typical shared memory architecture, where each of the processor contained write-back caches. In write-back caches, we noticed that the values written back to the memory depend on which cache flushes or writes back the value and when it does so. We also noticed that the cache coherency problem exists even on uniprocessors, and on uniprocessors this is due to the interaction between the caches and the I/O devices. However, in multiprocessors the problem is performance critical, where the order among the multiple processors is crucial. From this, we mean that for single shared memory with no caches, a serial or total order is imposed on the operations to the location, and for single shared memory with caches, the serial order be consistent, that is, all processors must see writes to the location in the same order. Considering this, we can say that in a coherent system, the operations issued by any particular process occur in the order issued by that process, and the values returned by the read are the values written by the last write to the location in the serial order. Then we talked about the write propagation and write serialization as the two basic features of the coherent systems. We also noticed that to implement cache coherence, the multiprocessors extend both the bus transaction and the state transition. The cache controller snoops on bus events, that is, write transaction, and invalidate or update the caches. Then we discussed the cache coherence protocols, which use different techniques to track the sharing status and maintain coherence for multiple processors. The two fundamental classes of coherence protocols were defined as the snooping protocols and directory-based protocols. While talking about snooping protocols, we noticed that all cache controllers monitors or snoop on the bus to determine whether or not they have a copy of the block that is requested on the bus. Whereas, while introducing the directory-based protocols, we said that the sharing status of a block of physical memory is kept in one location called directory. We discussed in details the snooping protocols. Here we said that the snooping protocols are implemented using two techniques, that is, write validate and write broadcast. Then we discussed these techniques and noticed that the write validate method ensures that the processor has exclusive access to the data item before it writes that item, and all other cached copies are invalidated or cancelled on write. Whereas the write broadcast approach, on the other hand, updates all the cached copies of a data item when the item is written. We also noticed that the invalidate scheme requires one transaction for multiple writes to the same word, and it uses special locality, that is, one transaction for write to different words in the same block. Whereas the broadcast technique offers lower latency between the write and the read. Then at the end, we discussed the finite state machine controller implementing the snooping protocols. The state machine controller responds to the request from the processor as well as from the bus. This response is based on the type of the request, its hit or miss status in the cache, and state of the cache block specified in the request. Furthermore, over here, each block of the memory is in one of the three states, that is, the shared state, exclusive state, or invalid state. The invalid state means not in the cache, and each cache block tracks these three states. Now today, we will continue our discussion on the finite state machine controller for the implementation of snooping protocols. And here we will try to understand the working of the finite state machine controller with the help of a typical example. In this example, we assume that two processors, say P1 and P2, each have its own cache and it shares the main memory connected to the bus. The status of the processors, the bus transaction, and the memory is depicted here in a table for each step of the state machine. Here, the state of the machine for each processor and cache address and the value cached and the bus action and shared memory status is shown for each step of the operation. Here we assume that initially the cache is in invalid state. That is, the block of memory is not in the cache and the memory blocks A1 and A2 map to the same cache block where the address A1 is not equal to the address A2. Now let us see stepwise how the state machine works and what changes occur in the table. At step 1, which is corresponding to the P1 writes a value 10 to the location A1. Here, the write miss on the bus occurs because initially the cache is empty and the state transition from invalid to the exclusive state takes place. That is, the first change in the state diagram is the transition from the invalid state to the exclusive state. At step 2, as you can see over here, it relates to the operation that P1 has to read A1. Here, the CPU read hits occur, hence the finite state machine stays in exclusive state, whereas at step 3, that is P2 reads A1, here different actions are done. As P2 is initially in invalid state, therefore read miss on the bus occurs. The controller state changes from the invalid to the shared. Secondly, P1 being in exclusive state, the remote read write back is asserted and the state changes from exclusive to shared. And thirdly, the value 10 is read from the shared memory at address A1 into the processor P1 and P2 caches at A1. And both the processors P1 and P2 controllers are in shared state. At step 4, which is P2 writes a value 20 to A2, the processor P1 finds a remote write, so the state of the controller changes from the shared state to the invalid state. And as P2 finds a CPU write, so it places write miss on the bus and changes the state from shared state to the exclusive state, and it writes the value 20 at A1. And also the memory address is A1 with the value A1 over here. And lastly, at step 5, which is where P2 writes a value 40 to A2, the processor P2 being in exclusive state, the CPU write miss occurs and it initiates write back to P2 at A2. Furthermore, the processor P2 remains in exclusive state with the address A2 and value 40. With this much discussion onto the implementation of finite state machine for the snooping protocol, let us discuss some implementation complications. Here in this example, we have observed that the finite state implementation of the snooping protocol normally works well. However, the following complications have been observed. Number one, the write races and intervention and invalidation. The write races occur when one processor wants to update the cache, but another processor may get the bus first and then write the same cache block. We know that the bus transaction is in two steps, that is the arbitrate for bus and to place miss on bus and complete the operation. Now, if miss occurs to the block while waiting for the bus, it handles miss, that is invalidate, and then restarts. Furthermore, to overcome the write races, we split transaction bus so that it can have multiple outstanding transactions for a block and multiple misses can interleave, allowing two caches to grab block in the exclusive state, and lastly, it must track and prevent multiple misses for one block. Now, let us talk about the snooping cache conflicts. In snooping cache method, the CPU accesses the cache and the bus transactions check the cache tags. The processors continuously snoop on address bus, and if the address matches the tag, it either invalidate or update. Since every bus transaction checks the cache tags, therefore there could be interface with the CPU. So there are two ways to reduce the interference, and these two methods are: number one, duplicate steps of tags for level 1 caches. That is, here the CPU uses a different set of tags and the CPU gets stalled during cache access when Snoop has detected a copy in the cache and tag needs to be updated. Secondly, we can have multiple level caches with inclusion. That is, the level 2 cache already duplicates provided L2 obeys inclusion with level 1 cache. Here, the contents of primary cache, that is L1, is in the secondary cache, that is the L2. And most CPU activities are directed to level 1 cache, and the Snoop activity is directed to level 2 cache. If the Snoop gets a hit, then it arbitrates the level 1 cache to update and possibly get the data. This will stall the CPU. However, it can be combined with duplicate tag approach for further reduction of the conflict or contention. In order to overcome these conflicts, number of variations have been proposed in snooping caches. The variation referred to as the MESI protocol is one where the protocol contains 4 states instead of the 3 states of the snooping protocol. These 4 states are referred to as the modified state, the exclusive state, the shared state, and the invalid state. Here, in this particular protocol, the exclusive means exclusively cached but clean upon loading. Here, the bus serializes writes. Getting bus ensures no one else can perform memory operation, and on a miss in a write-back cache, we may have the desired copy and it is dirty, so it must replay, and it adds extra state bit to cache to determine whether it is shared or not. So these are a few modifications which are suggested to the existing snooping protocols. Here we add the 4th state, modify, which modifies for exclusive writes. Another variation to the snooping cache protocol is known as the Berkeley protocol. The main idea of the Berkeley protocol is to allow cache to cache transfer on shared bus. It adds the notion of the owner. That is, the cache that has the block in a dirty state is the owner of the block. The last one who writes is the owner. The owner is responsible to transfer data if read occurs and to update the main memory. If a block is not owned by any cache, then the memory is the owner. Here is a summary of the snooping cache protocol variations. Here you can see that the basic protocol has got 3 states, that is the exclusive, shared, and invalid. Whereas the Berkeley protocol has 4 states, that is the owned exclusive and the owned share. Whereas the other 2 states are the same, that is the shared and invalid. Here the owner can update via bus invalidate operation, and the owner must write back when it is replaced in the cache. The other variations are referred to as the Illinois protocol and MESI protocol. The Illinois protocol suggests 4 states as the private dirty, private clean, shared, and invalid. Here, if read is secured from memory, then the private clean state occurs. If read secured from other caches, then the shared state occurs, and it can write in cache if it held private clean or dirty. Whereas the MESI protocol has got 4 states known as modified, and it is a private memory modified. Exclusive, that is private memory is exclusively used. The shared means shared memory, and invalid means not in the cache. Here is the finite state machine representation of the 4 states of the extensions to the snooping finite state machine, which we discussed earlier. Here in this case, the Berkeley's 4th state shows the ownership. The shared is referred to as the modified. It need invalidate only or upgrade the request, and it do not allow to read memory. Whereas the MESI protocol clean exclusive state provides the miss for private data on write, and the Illinois protocol, the caches supply data when shared state no memory access. So now let us talk about the coherence problem in case of larger processors. The larger microprocessors use separate memory per processor. The local or remote access is via the memory controller. One cache coherency solution is using non-cached pages. However, the alternative approach is to use directory that contains information for every block in the memory, and it tracks the states of every block in every cache which have copies of block, that is dirty or clean, etc. The use of information per memory block versus per cache block has some plus or minus points. The plus point is that the memory provides simpler protocol as compared to the centralized or one location memory. Whereas the minus point over here is that the directory is function of memory size rather than the function of cache size as in case of simple protocol. Now, with this much introduction about some variations in the protocol for shared memory and the consideration of this coherence problem for larger processors, we will be talking about the directory-based protocols for distributed shared memory system. The directory-based protocol is similar to the Snoopy protocol because this protocol also has got three states. The directory-based protocol are the shared state, the uncached state, and exclusive state. The shared state is one where we assume that one processor has data and it keeps the memory up to date, whereas the uncached states represents that there is no valid data in any cache. So basically no processor has this state, whereas the third state, that is the exclusive, represents that there is only one processor which has data, and this processor is the owner, and this state in fact represents that the memory is out of date. In addition to the cache states, the directory-based protocol must track which processor have data when in the shared state. Usually it uses a bit vector which is 1 if processor has a copy, otherwise it is 0. Furthermore, the directory-based protocol keep it simpler to write to non-exclusive data in case of write miss. The processor blocks until the access is complete and it assumes messages received and acted upon in order. Furthermore, in directory-based protocol, no bus want to broadcast, and it interconnects no longer simple arbitration point. All messages have explicit response. Typically, in case of directory-based protocol, 3 processes are involved, and these processes are the local node. The local node is one where a request originates, and the home node is one where the memory location of the address resides, while the remote control has a copy of a cache block, whether exclusive or shared. Now, in order to understand what are different messages which are passed on while implementing the directory-based protocol, we will consider some example messages, and we will explain how these messages are being passed. These messages may be defined with the help of different attributes and different operations associated to it. For example, let us consider the first message is of type read miss. The source of this message is the local cache, and its destination is the home directory, whereas the message contents are the processor number and the address. Here you can see that the processor reads data at address A, and it makes the processor a read sharer, and it arranges to send data back. The second type of message is the write miss. The source of this message is once again the local cache. The destination is the home directory, and the message contents are the processor name and the address. Here the processor writes data at address, and it makes the processor the exclusive owner, and it arranges to send the data back. The other message types are invalidate, fetch, and fetch or invalidate. In these messages, the source is home directory, destination is remote cache, and the message contents are the address. In case of invalidate message, the invalidate shares a copy at address A, whereas the message type fetch fetches the block at address A and send it to its home directory, and the message of type fetch or invalidate, it fetches the block at address A and sends it to its home directory and it invalidates the block in the cache. The other type of messages are the data value reply and the data write back. The source of the data value reply is the home directory. Its destination is the local cache and the message contents are the data. This message returns a data value from the home memory and it basically responds to the read miss. Whereas the message type data write back has the source remote cache and its destination is the home directory. Whereas the message contents are address and data. It writes back a data value for address A and it invalidates the response. Now, with this much discussion onto the directory protocol messages, let us look into the state transition diagram for an individual cache block in a directory-based system. Here you can see that the states are identical to the Snoopy cases. The transactions are very similar. The transactions are caused by read misses, write misses, invalidate, or data fetch request, and it generates read miss and write miss messages to home directory. Furthermore, here you can note that the write misses that were broadcast on the bus for snooping results in explicit invalidate and data fetch request. Here you can note that on a write, cache block is bigger, so it needs to read the full cache block. Here you can see that the same states and structures are shown as the transition diagram for an individual cache. However, the two actions performed are: number one, update of directory state, and the send messages to satisfy the request. Here the controller tracks all copies of memory block and also indicates an action that updates the sharing set. This sharing set is called sharers, as well as it is sending messages. Now let us consider the example directory protocols. Here you can note that the messages sent to the directory cause two actions, that is, update the memory and more messages to satisfy the request. The block is in uncached state, that is, the copy in memory is the current value and only possible requests for the blocks are the read miss and write miss. Now let us see what do we mean by the read miss. The requesting processor sent data from memory and requester made only sharing node, so the states of the block made shared, whereas the write miss means the requesting processor is sent the value and becomes sharing node. The block is made exclusive to indicate that the only valid copy is cached. Sharers indicates the identity of the owner. The block is shared state means that the memory value is up to date. Here the read miss and write miss activities are as follows. The read miss means the requesting processor is sent back the data from the memory and the requesting processor is added to the sharing set. Whereas in case of write miss, the requesting processor is sent the value. All processors in the set sharer are sent invalidate message and sharer is set to identity of requesting processor. The state of the block is made exclusive. The block is exclusive means that the current value of the block is held in the cache of the processor, which is identified by the set sharer, that is the owner. However, here the three possible directory requests are the read miss, the data write back, and the write miss. The read miss means that the owner processor sent data fetch message causing state of block in owner's cache to transition of shared, and it causes the owner to send data to directory where it is written to memory and sent back to the requesting processor. Furthermore, in the case of read miss, the identity of requesting processor is added to the set sharer, which is still containing the identity of the processor that was the owner, since it still has a readable copy. So we can say that the state is shared. Whereas the data write back is one where the owner processor is replacing the block and hence it must write it back, making memory copy up to date, and the block is now uncached and the sharer set is made empty. The write miss is such that here the block has a new owner. Here, a message is sent to old owner, causing the cache to send the value of the block to the directory from which it is sent to the requesting processor, which becomes the new owner. The sharer is set to identity of new owner, and the states of block is made exclusive. Now, today we have completed our discussion onto the symmetric shared memory and distributed shared memory type of multiprocessors. We have discussed in details the cache coherency problem, and then we discussed different protocols to overcome these problems. Here we notice that the caches contain all informations on state of cached memory block. The snooping and directory protocols are similar. However, the bus makes snooping protocols easier because of broadcast. Furthermore, while talking about the directory-based protocol, we notice that the directory-based protocol has extra data structure to keep track of states of all cache blocks. Now, with this much discussion, we close the discussion onto the parallel processing, and from next time we will take up the interconnection of different processors. Till then, Allah Hafiz.